All right, so imagine that your data set is somewhat like maybe something like this. Some are a little above, some are below. You can approximate this data using a linear regression, right? But it may not do justice. So I think many of you did this physics experiment where you would drop a ball and look at its height, how it goes down, right? And then the formula for the height would be something like the height of the ball would be like y0. Oh, let's put y0 at the end. It's like negative g over 2 t squared plus initial v0 t, and then plus your y0, right? So that's the formula for something that, let's say you threw something up and it came down, right, at each point. Now, if you use some high-speed camera to measure the position with t, what you're going to get is not exactly this value, but with some error, right? Because the error in measurement, and there's some, like the speed of the camera might not be always exact. So you would get something like this. And then if you want to get a nice approximation, the line wouldn't do it justice, right? So you might have to use a quadratic approximation. So instead of trying to approximate this data, so let's say these values are t values and these values are y values, and then let's say you have some y1 t1 y1 value here, and then t2 y2 value here, and then something like that. And if you just say y hat, your prediction is some a plus b t, that's really not a good idea, right? It just ignores the physics. So the better approximation you probably want would be y hat equals to a plus b plus bt plus c t squared. So those are the cases where you would use polynomial approximation. Now, however, what I want to tell you is that polynomial approximation is nothing more than multiple linear regression, because what you can do is you can just call this one t as your x1 and this t squared as your x2. Then suddenly this seemingly complicated looking polynomial regression is really nothing more than a multiple regression of x1 and x2. Do you agree? Right? Yeah. So that's the demonstration I want to show you in this next one. Okay? Pi again. And then once you have your NumPy imported, I'm going to make T as a linear space, np.lin space. What it does is it takes an interval and it gives you back endpoints of the interval if you divide it into n equal intervals. So actually, you have to provide the number of points that you want, and then it will give you equally spaced points in that interval. So what we are going to do is we're going to ask for 0 to 10 seconds. And then we're going to have it in 5 seconds, no, 0.5 seconds increments, okay? So if you have 0.5 second increments, then you have 10 divided by 0.5, that's 20, but because there are endpoints, you have to add 1. So if you divide by 21, if you do this, let's see what's in there. Then you get this nicely equispaced values from 0 through 10. 0.5 apart. So that's going to be our t value. Okay. Now, what I'm going to do is I'm going to make y using that formula. And let's just say g is like negative 10 meters per square second, okay, rather than 9.8. Okay, so we'll just say negative 10, which is negative 10 over 2. That's g over 2, right? Negative g over 2 times t squared. And squared in Python is double asterisk, okay? Okay, so that gives you t squared. Plus, let's think about a model where you threw the ball upwards by, say, initial speed 5 meters per second. Okay, so 5 times t. And then let's also say that this ball was thrown from the top of a building that's 20 meters high. Something like this. Okay. So if you do this and then to see what's going on, let's try to plot. In order to plot, we need to use the matplotlib package. So we're going to do from matplotlib import pyplot. That will be the package inside the matplotlib we use mostly. But because pyplot is long, we're going to rename it as plt. Okay, and then once plt. I don't know why. No. Okay. All right. And then now I'm going to plot x and y to see what the graph looks like. Did I have t and y? Yeah, it's t and y, not x and y. Plot t and y. Shift enter. What's the problem? Oh, right. plt.plot. Okay. Okay, good. So, I don't like that it's like almost parallel and comes down. Let's make the initial velocity a little bigger. Let's put like something like 10. Okay, sorry, I went back and just replaced this by 10. If you're doing spider, you can do up arrow to find all the previous commands. Okay, and then let's plot this again. It's still not good, but I can live with this one, right? So that's what we have. But you know, this will be only the ideal case. If we had a real life situation and we took high-speed camera to take multiple pictures, it doesn't look like that. It will have some error, right? So what we're going to do is we're going to say y error is like y plus, we're going to add some error terms, and we're going to make use of the random. We talked about random before, right? And inside the random, np.random, sorry, numpy.random. Inside the numpy.random, there's the normal package, which gives you random numbers that's normally distributed. So something that's close to 0 is the most likely number that it produces, and getting a number like 2 or negative 2 or 3 or negative 3, those are very highly unlikely, right? If you know the standard normal distribution, you know that the chance of getting a number that's more than 2 sigma away from the average is what? Do you remember that?
2 standard deviations?
Yeah, away from
It's under 95%.
95%, yeah. So 95% of the time you get a number that's inside the 2 standard deviations, right? So if you use this, 95% of the time, the value that it generates, the random number it generates will be between -2 to +2. And then in some rare cases, you might get some numbers that are bigger than that, okay? So that's what we are going to do. The thing is, if I just call this once and add to this, then it just adds a single number. That's not what I want. See, y is you can see here, it's ND array with shape 21 comma. It means that it's a size 21 row vector. So I should actually generate 21 of them by saying size equals to 21. And because I want the number errors to be somewhat bigger than just plus minus 1, let's multiply something like 5. Okay, so that's my imperfect real-world measurement of y. Let's try to compare the two. So we're going to do PLT dot plot t comma y, and then PLT dot scatter t comma ye. Now, the reason I do scatter is because if you do plot, then it connects all the values. So that's not what I want. I want a scattered plot. Yes?
Is it like a line of best fit?
We are trying to get the polynomial or the quadratic function of the best fit later by doing this polynomial regression that we're doing. Right now, we're just comparing the original ideal function with the supposedly error-prone YE, okay? So let's see how they compare. You see that it's kind of distributed above and below. Yeah, I think 5 is still not enough. Let's make it bigger. Let's make it like 10. Okay. Okay, so that's more like it, right? That's more real world like. It sounds a little suspicious there, but let's just say that's what we have, all right? Okay. So now what do we do? Well, let's first do the linear regression. See what happens. So from sklearn dot linear model import linear regression, and then we are going to fit this one LR equals to linear regression dot fit, and then t and y. That's what we want to do. However, there's something that we still have to do. We want the t, your predicted variables should always be a column vector, okay? Column of data. That's what the folks making the linear regression package made, right? So if you have the wrong dimension, if you feed a row vector for the prediction variables, then it complains. So you have to do the reshape, okay? So reshape. And let me explain the -1, 1 again. I just said -1, 1 is, it gives you a column vector. In Python, in NumPy package, every time you put a -1 in one of the positions, that means that's a missing thing you have to figure out. So for us, we actually know what the shape should be. It should be 21, 1, right? Oh, by the way, when you put this in the reshape, you have to put in another parenthesis, okay? So, oh, sorry, 21, 1. So that could be it. You could put it like that, but then who has the time to go back and see what the dimension of t is and then put that 21 there? You want the NumPy to automatically figure that out, right? And when you want to do that, that's when you put -1. If you put -1, it's like saying, hey, hey NumPy, I need the second part to be 1. Just figure out what should be in this empty place. And you feed in -1, and NumPy automatically populates that with 21, right? So that's like a hand to just quickly make a vector into a row vector into a column vector. Okay, so we do this and we fit it, and then let's try to draw the graph. So now we're going to copy what we had before, but we are now going to draw 3 things. So I'm going to copy this thing here. And on top of it, we need to do plt.plot of t comma, and then we're going to use the prediction of LR. So LR.predict using the t values. But again, we can't just provide the t-values. We have to reshape it as a column vector. So let's put that column vector in here. Let's graph everything. And now you see that this orange line is the linear regression doing an awful job, whereas the original model is much better, right? So that really is yelling that you shouldn't be doing this. You should really do the quadratic regression, which is just the multiple regression with an added column. So let's do this. Now we are going to make a new set of predictors. So new t is going to be made out of the old t, but then we're not just going to use the t only. We're going to use a t and then t squared. How's that, right? So if we use that as the predictor, then doing multiple regression with that is same thing as doing the quadratic regression, right? So that's what we do. And then make sure we have this correct shape. Let's look at the shape. And it's not good. That's like 2 rows and 21 columns. We need the 2 columns for it to be correct. So let's define it differently. We're just going to do the same thing, but we're going to do the transpose because it's in the wrong direction. Okay. So that's going to be our predictor, ut. And now we can do the regression again. We already imported the linear regression package, so we don't have to do it again. Linear regression is already loaded up. We execute this with fit new t to the y values, actual y values. And now let's try to plot. So just go up and copy the entire thing. Paste it over here, but instead of LR predict t, we're going to use the new t to predict. Okay, so I'm going to use the new t to predict. Let's plot it. Oh, what happened? Basically, the blue curve and the orange curve is the same thing. Yeah. So our regression did such a good job that it basically recovered the original value. Right? So you can kind of see that from engineering perspective, this is very important because let's say you're trying to measure the car's velocity and acceleration accurately, right? Then how would you do it? You do a quadratic regression, and then you read off the coefficients of t squared and t just by doing this. Then it gives you a very accurate measurement of your acceleration and velocity. Yes? Okay, yeah. So I mean, this has a very practical value for engineers. Anytime you have a sensor to figure out the movement of something from the positioner's position using camera, you need to do the quadratic regression to accurately figure out what the acceleration and velocity is, because just simply taking 2 points and dividing by time, you think that's going to give you a good approximation of the velocity, but no, because the real world always has errors. And to overcome those errors, you need to know how to do these linear regression, okay? All right, so that's all for today.